Hello, so today we are going to do this daily challenge, largest submatrix with rearrangement. So the idea here is we have a submatrix of 1 and zeros, and we want to get the largest submatrix where every element is 1. And what we are allowed to do here is reorder the columns optimally. So we can change the order in whatever way we want so that we get the largest submatrix. Okay, so if we look at the first example, what we can do here is we can take this largest number of ones and put it in the middle. That way, basically, we get this as the largest submatrix. And so the area here is 4. Another option is to also put this one first and then the second one in the middle. That also works, but we get the same area. This is also one note here about this is Leetcode sometimes give you the first example in a way that is to mislead you a little bit from the solution. For example, in this case, they put the one with the largest number of ones in the middle instead of in the first position. Even though this solution gives you the same area, you will see later in our implementation of a solution here is that it would be easier to put it in the first position, to put the column with the largest number of ones in the first position. Okay, so that's sort of the idea here. Now, if we look at the constraint, we have 10 to the power of 5. So this tells us we need an O(n) solution. O(n) being basically m by n. So basically, in order of the size of the submatrix. Okay, so let's see how we can optimize, implement this. Okay, so how do we actually handle this? So with any like submatrix triangle, like what we are looking for here, what matters with an area? That's what we are trying to maximize. We are trying to maximize the area. So what matters here for an area? Well, area is based on the width or the base. So this can be called either width or base, multiplied by the height, right? And so how do we, what you want to do to get the maximum area, because the area is just going to be the width multiplied by the height. So how do we maximize it? Well, you maximize each one, the width and the height, right? To get the largest submatrix. So that's the first idea to keep in mind here. And so now the core idea is, okay, how can we maximize these? Well, we do know that we can rearrange the columns. So we can, for example, put this one in front. So we can end up with something like having one here, all the 3 ones first, and then having this one with the most ones next, and then 0. So we can change the order of the columns, but we can't change the rows. We can't decide to, for example, take this and move it here. We can decide to say have 1 1 1 0 1 1 0. That we can't do that, right? We can't change the order of the rows. And you can see also if you change the order of the rows, that impacts what the triangle, the maximum triangle is, because if you take a look at this one, the maximum submatrix is actually here. If we change the order of the rows, now the maximum one we can get is actually this one, right? But in another matrix, maybe reordering the rows gives us a larger one, but we can't do that. We can't reorder the rows, okay? So that's something to keep in mind here. Okay, so with this, how can we use it? But now the question becomes, okay, why do I decide to put this, the largest number of ones in the beginning? Is that helpful at all? Well, to do that, let's first do sort of a prefix sum, because, well, how do we know that a position gives us the largest height, right? Well, the position that has the maximum number of ones gives us the largest height. And so let's just do the prefix sum. So if we do the prefix sum with resetting at 0, right? Because let's say you have 1 0 1 1 1 1 0 0. Well, this one you have, if you do the prefix sum, you have 1 2 0 0 1 0 1 2. You need to reset at 0 here. You can't do like the normal prefix sum where you'd have 1 1 2 3, because this is misleading, because you can't take, for example, you can't take this as a submatrix because you have a 0, okay? And so you need to reset at 0 for this prefix sum, okay? And so how do we, so let's do that, let's apply that to this matrix here. Let's do the prefix sum like this. So let's copy this, move it here. Okay, so if we do the prefix sum with the reset, then we'd have 0, 1, the prefix sum on each column, by the way, by column. Okay, so 2, 0, 1, 0, 1, 2, 3. So immediately now, by looking at just one single position, you know that you have the largest height of the column ending at that position. So that's the benefit of doing this. First, the prefix at 0, okay? Okay, so now if we look at this, what do we see? Well, we first see that, for example, for this row, it's sort of problematic because of this 0. This 0 is getting in the way, right? It's not allowing us to get, for example, this here. And so, since we are allowed to rearrange the columns, let's just sort. Now, sort by what? Well, let's sort each row by, let's just sort each row. Now you may say, okay, if we sort each row, would the columns sort of, would like the first position of the column be here and then the second position be here? Would that be sort of not actually sorting by columns? But the answer is no, because we are taking the sum, the prefix sum. So if this one is larger, right, that means this one was had a 1, right? And so if we put this one here, we will end up putting this one here, 1 as well, because we sort in decreasing order every row. And so if we do that, so this is basically the prefix with reset. Now here, let's do the sorting. So if we do the sorting, at this point, we would have 1, 0, 0, 2, 1, 1, 3, 2, 0. So you can see each column actually remained the same. This column here went here. This column here went to the end. This column here went here. So sorting by each row is going to be the same as sorting, basically like rearranging the columns. So that's a key idea here as well. Okay. Okay. So now knowing this, what do we do next? Okay. So now that we have it sorted, how can we get the largest area? Well, now it's very easy, because since we know this has the most ones, right? We can just go through our rows, right? So we can just go through each row and calculate the area. So for example, at this position, what would be the area? Well, the area is going to be the number of ones, which is what we have in this position. So let's call this ones, and let's say r now is equal to 0, then it's going to be just ones at position 0 for the row, and then column 0. So this would be the height, because that's the number of ones. So this would be the height. Now what would be the width? Well, the width is, this is column 0. The width is just the column. If we are at column 1, the width is going to be the entire thing. If we are at column 2, the width is going to be the entire thing. And so the width is just actually columns plus 1, right? Okay, and so that means basically that, so that means basically here, the width is going to be just columns plus 1, which is going to be 0 plus 1. Okay, so the formula that we are going to use is going to be ones at position RC multiplied by C plus 1. Okay, and so here the area is 1. Is that the max area? No. So we proceed, we check here, the area is going to be 0 because we multiply by 0. So we proceed here, 0. And then we go to position row 1. Then we go now, let me just put this down here. So now we go to row 1. So it's the height is going to be 2, because that's the number of ones we have, multiplied by the width, which is going to be column plus 1, so 1, so it's 2. So the max area now is 2. We go here. What's the height? The height is 1. What's the width? Width is C plus 1, so it's 2. And that's actually what you see here if you do this, because this means that you have a 1, 1, 1. So the max submatrix is just this one, which is 2, which is what we have here. So, and then if we go forward a little bit more, so if we go forward to this position, then it's going to be 1 multiplied by 2 plus 1, so 3. So we have now 3, and that's actually just this entire thing, right? Now, why are we able to do this? Why are we able to just multiply by the value here? Because we know that the previous column had a larger number of ones at this position, right? Because we sort by the larger, and so that means we can. This one is the minimum. So if you have, like, let's say something like this with 1 1 1, and then something like this with 1 1 1, you know that at least you can do this entire thing as a submatrix because this has a larger number of ones, right? If you let's say have now 1 1 1 here, then you know you can do this one, right? Sorry, this is not super clear. You know that you can at least do this one because you are guaranteed that this one has more ones at this position. So the height, that means basically this. If the sum here is larger, that means you at least have these. And so that's sort of the idea here of using C plus 1 as the width. And so we continue, we go here. So what does this mean? That's 3 multiplied by 1, so 3. And then when we go here, that's 2 multiplied by 2. So now we have 4. And this is exactly the solution of, if we reorder, we get this, right? So put that 4 there, and then when we go here, it's multiplied by 0, so it doesn't matter. So this is the optimal solution we get, okay? So that's sort of the idea of the implementation. Now, what's the time complexity here? Well, we are doing an O(n) by n first to just do the prefix sum here with a reset, so because we go through each position. So this is O(m) by n first, and then we do the sorting. So for each row we sort, right? So if we say m is the number of rows, then it's going to be m log of n because we sort each row, okay? So it's going to be mn plus m log n. So that's our time complexity. Now let's implement this solution and make sure it passes. Okay, so let's implement this solution. So first we need just to get the size of the number of rows and the number of columns. We'll need this for later. And now let's do our prefix sum in another separate array. Of course, you can do this like in the same matrix one, but just to make this more clear, I'm going to do it in a separate one. Of course, that would mean extra space complexity. And now this is going to be in range of rows, okay? And then what we do is we go through each column so that we can record the prefix. Remember, the prefix sum is going to be calculated by columns. And so once first we know that the first position, right, is going to just be matrix of 0, right? So the first row, for the first row, it's going to be just the same values because there is nothing before. And now for each row, we can start from 1 because we already handled the first row. And so this is going to be just the number of rows. Then ones at RC are going to be equal to the previous row, the same column, right, plus 1, but only if the matrix at that position actually has a value of 1. Otherwise, we want to reset. So to reset, we just set it to 0. Okay, so now that we have our sort of modified prefix sum, we can just go for each row. Remember, we want to sort each row in decreasing order. So that means we sort in decreasing order. Let's just use refers in Python. And then for each column, right, we want to calculate the max area. That's what we did in the overview. For each position in the row, we calculated the max area that gives us. Now we of course need to initialize the max area, so to 0. That's what we return at the end as well. And then here, our max area, we are going to take the max with max area and current area. Now we need to calculate our current area. And we said current area is just height multiplied by width. So what is the height? We said that the height is just going to be the number of ones from our prefix sum, because that tells us how many ones we have up. So that's the height. And then the width, we said, is going to be just C plus 1, because we are guaranteed that anything before this C has more height, so has a larger height. So we at least would have same height that we that can be contributed to our submatrix here. So that's why we do C+1. And yeah, that's pretty much it. Now we can, this was just for clarity, we can simplify it here to be like this. And we can simplify it even further like this, okay? And now we can run this and see if it works. And looks like it did, so let's submit. And this passes, okay? Yeah, so that's pretty much it for this problem. Thanks for watching, and if you need one-on-one coaching for your coding interview, please click on the link in the description. See you on the next one. Bye.